Alright, so welcome to this video where we're going to be looking at measurements and their errors. This tends to be the first topic in A-level physics that is taught to students. It is the first topic on the actual specification, and it is quite an important one because it is something that crops up again and again, and it basically deals with how we actually take our measurements and how accurate we can call our measurements. And there's a whole range of terms that we're going to run through, and the reason why it keeps cropping up is because whenever you do an experiment, and in physics we do tend to do experiments, you need to know basically how to take measurements in your experiments in the best possible way, and also to understand what the quality of the measurements you're taking actually are. And so let's dive straight into it then. So the first thing we're really going to look at under this topic is actually the concept of a standard set of units. Okay, so we call this the SI units. Now, what do we mean when we say SI units? Well, the whole concept of the SI units, the standard international units, is the idea that we want to use the same unit for each measurement, and that way we can basically compare measurements really easily between different experiments, between different scientists. They know exactly what measurements they're talking about, they know what units they're using, and that you avoid all these kind of confusion. And so if you can imagine, if you take something like length you can measure in a range of different ways. You can measure it in kilometers, you can measure it in miles, you can measure it in feet, inches, yards, all these kind of different measurements. And if you imagine if we had scientists using all those different ones, it could become quite confusing. So what we have instead is this base that we use of a standard set of units that everyone has kind of agreed to use. Now, the SI units we can actually split up into two types. Now, the first type we call the fundamental or the base units. And the fundamental units basically deal with a few different measurements. So the first one is actually time. So time we measure in seconds. Distance, we always say we're going to measure distance in meters. Mass is always measured in kilograms. The next one is electric current. Electric current you've probably seen before. We always measure in amperes or amps. The next one is amounts of substances. Now that's an interesting one. You probably come across this in chemistry, GCSE. That is moles. And the last one that we have is actually the length, which we already talked about. And the length, as we mentioned, there's all types of ways you can measure it, like there are for all of these, but we measure it in meters. Cool. So those are the ones that you actually do need to be aware of. Those are the fundamental base units. From those, you can actually have the derived SI units. So we'll just go through the derived ones. But the idea is that if we define all of these quantities, then any other quantity we can also formulate an SI standard unit using these fundamental base units. So what do we actually mean when we say something like that? Well, let's say we want to measure something that isn't one of these 6 things, that we actually want to measure acceleration. And you're thinking, well, acceleration, then we haven't agreed on a standard unit. So say if people start using different units. Well, this is where we get to the idea of the derived SI units. And so acceleration, we know the formula for acceleration essentially is the change in speed over time. Or to be more accurate, we'd say instead of the change in speed, we could say the change in velocity over time. And that's fine. Now we need to understand velocity. Well, again, time is a fundamental unit. It does have a fundamental unit, that is seconds, but velocity doesn't. So now we look at velocity. Now velocity is actually, what's the formula for velocity? It is distance over time. So to keep things a little bit simple, we're just going to call this speed instead. But essentially it's very similar if you use velocity. But so speed, now we've split that into distance over time, and now you can see actually we've got our SI units. We've got this is in seconds and this is in meters. To work out the standard units for speed, then it would just be the distance over time is just meters over seconds. And we can actually write this in slightly different format. So we can use indices instead, and this is very common in your exams and in any textbooks that you come across, and it'll be written like this in your exam papers. So here we've written meters seconds to the -1, and that just means the same thing as meters per second. Basically what we've done is we've rewritten this s, this is equal to 1 over s, which is equal to s to the -1. And you should know that from your maths, but that's basically where that comes from. So now this is the standard international unit for speed. So this is the SI unit for speed. So next we want to see, okay, well now we've got the SI unit for speed. How do you then use that to find the SI unit for acceleration? Well, we do the very, very similar thing to what we did in the equation before. So we've got speed, or change in speed over time, equals acceleration. We'll just shorten that there. And now we can plug in the units for both of these. So the unit for time is speed, the unit for time is seconds, and the unit for speed is, we just worked out, is meters per second. So now we have meters per second over seconds, if we just look at the units by themselves, and that gives us meters per second squared. Which you should know, or you should be familiar with. That is the unit we use for acceleration, meters per second squared, and we've just rewritten it. These are the same thing basically, in a different format. So that is then the standard international unit for acceleration. So at the SI unit for acceleration is equal to meters per second squared. What these are is basically derived units. We've derived the SI units for different quantities using the fundamental base units. So hopefully that makes sense. So that's your SI units essentially. The next thing we want to learn about is the actual prefixes that we use. So the prefixes are basically when we have very large or very small numbers, it's useful, instead of actually writing the whole number out, we can use a prefix. And you're familiar with prefixes already. For example, if we were to write 100 millimeters, now technically we could write this as meters instead, but 100 millimeters is a bit easier to write than meters, because 1 millimeter is equal to 0.001 meters. As we've seen the same thing with centimeters. So 1 centimeter equal to 0.01 meter. So if you imagine then, if we were to take measurements of 10 centimeters, but we didn't have this prefix centi, the C here, then we'd have to write 10 centimeters as 0.1 meters. Or as you can imagine, as we get to very small quantities, we don't want to be writing out 0.00001 meters all the time. So instead what we do is we introduce this idea of prefixes. So you do need to be aware of a few different prefixes. And the way we're going to define the prefixes here is using standard form. So standard form is when we have a number written like 1 times 10 to the power of 3. Now this is the same thing as writing 1000. Why is it the same thing? Well, 10 to the power of 3 is 10 cubed, is 10 times 10 times 10 is 1000. So all this is 1 times 1000, so it's 1000. But we write it in standard form because we can get very large numbers. So if you were to write 1 times 10 to the power of 10, then you can imagine we'd be writing 10 times 10 times 10 times 10, and you'd get basically 1 with 10 zeros behind it. So we don't want to be writing all that out, so instead we use standard form. And then instead of using standard form, we can actually use our prefixes, but each prefix basically maps to a specific number. So the first one we need to know about is T, or tera. Now tera is 10 to the power of 12. So what do you mean 10 to the power of 12? Well, we're saying that essentially if you have 1 terameter, you can say, you're saying you have 1 times 10 to the power of 12 meters. So hopefully that makes sense. And you see similar things with the other ones, so you do need to be aware of a few different ones. You've got G, which is giga, and that is 10 to the power of 9. You've got M, capital M, which is mega, and that is 10 to the power of 6. You've got kilo, which is K, and that is 10 to the power of 3. So if you think of a kilogram, that is 1 times 10 to the power of 3 grams. So like I said, you should be familiar with a few of these already. You've got centi, which is 10 to the power of 2. You've got milli. Now milli is actually 10 to the power of minus 3. So when we say 10 to the power of minus 3, basically we're saying that this becomes 0.001. And you should be familiar with this from when you did your GCSE math, so it shouldn't be too much new for you here. The next one we got is micro. Now this one may be new. Micro is the Greek letter mu, and that is 10 to the power of minus 6. The next one we got is nano. Nano is 10 to the power of minus 9. Then we go to pico, which is 10 to the power of minus 12. And the last one we need to know is femto, 10 to the power of minus 15. Now, there's probably a lot there, but a few of those hopefully you should already be familiar with. But you do need to basically have these committed to memory, essentially. It can be a lot to remember, but hopefully if you get used to using them, then it should become second nature. But yeah, if a question says is 1 terameter or 1 gigameter or 1 nanometer, you should be able to translate that to the actual physical number and put that into a calculator to do any kind of calculations. So you do need to be familiar with those. Cool, so that is basically the measurement side. What we need to understand now is the quality of our measurements themselves. So we can take the measurements, but we can write them down now, but actually how accurate are those measurements, how precise are those measurements, what is the quality of the measurements, what do we mean by all of those terms? So essentially when we take measurements, there's always going to be some source of error. Now when we say there's error, that basically means that there is something that means that the measurement we get may not be 100% the true value. And we have certain errors that we need to be aware of. The first one is random error. Now again, this is something you should already be familiar with, really, random error. Random error essentially is error that can come from anywhere. There's not a specific source of random error, and most of the time there's not much that we can do to get rid of random error. You can never really get rid of random error completely. A good example of random error would be electrical noise within a circuit. So when you have a circuit like this, let's say you got a cell here and a bulb there. Now if you were to take a measurement within the circuit, you were to put an ammeter here. If you had a really sensitive ammeter, this ammeter would pick up the current, but would also pick up some electrical noise. Same thing if you were to put an oscilloscope in there, you're trying to measure the waveform of the current. Again, the oscilloscope would pick up some electrical noise. It's just random electrical energy within the circuit that is not to do with what you're actually trying to measure. So that is an example of random error. Now random errors affect precision. Precision is basically all about how close your measurements are together. So generally, if you were to take 3 different measurements, you get a spread, and if the spread is really close together, we'd say it's quite precise, and if it's quite far apart, we say it's not precise. So for example, if you were to measure the current within the circuit, let's say we measure it 3 times, 1, 2, 3, and the first time we get 0.5 amps, the second time we get 0.6 amps, and the third time we get 0.7 amps. Now the range between our measurements is 0.2 amps, and that basically is caused or can be caused by our random error, so something like the electrical noise within the circuit. Essentially that is what we're saying. If we were to have less random error, that would mean these measurements would be closer together, and if they were closer together, they would be more precise. So that's what we mean by this term precise or precision. Now in order to reduce random errors, what can we do? Well, the first thing and the most common thing by far is to take repeat measurements and to calculate a mean. Now the reason why we want to do this is because sometimes the random error, because it's random, it can be bigger in some occasions and can be smaller in some occasions. So let's say we were to take a 4th reading, and in this 4th reading we get a measurement of 2.5 amps. Now quite clearly we'll be able to see, because we repeated the reading 4 different times, this 4th reading is not accurate. But imagine that we only took the reading once, and we took the reading and we got 2.5 amps. We'd have no idea that this measurement here was caused by random error. We wouldn't know that it's actually not the measurement we're looking for, and as a result we would get something that's not accurate. Accuracy refers to the fact that the measurement is close to the actual true value. So if you imagine we're trying to measure the current in this circuit here, let's say we actually knew what the current was, right? Now technically we might not know that, but let's say we can work it out theoretically, and we know that the current should be let's say 0.6 amps, right? Now the accuracy refers to basically taking our measurement from the ammeter, how close do we get to that value? That's what we say when we talk about accuracy. Yeah, so if this was 0.7, then we say it's fairly accurate. Cool. So the idea then of reducing a random error, you can take repeat readings. You can 1, work out a mean. So you can 1, work out a mean, and 2, you can actually spot anomalies. So both of those very, very important. And of course, when you're working out your mean value, you can remove anomalies. So for example, we're working out the mean from these 4 measurements. We discount this 4th measurement and we just use the top 3. Cool. So that is basically random error. Another thing you could do to reduce random error is you could use something like a data logger or computer. So you want to use appropriate equipment that has the highest possible, will allow you to measure to the best possible accuracy, and something that is actually appropriate. And part of choosing the right equipment, so part of choosing the right equipment is this idea that you want to have something that is the correct resolution. Now, what do we mean by resolution? Resolution basically refers to the smallest possible measurement you can take using your equipment. So for example, if we were to take a ruler, and this ruler is graduated in centimeters, so this is 0 centimeters, and then this is 1 centimeter, this is 2 centimeters. Then basically each of these smaller ones in here, smaller graduations, is 0.2 millimeters, if I've drawn that correctly, and hopefully I have. And so the resolution here, we're saying you can measure to the closest 0.2 millimeters. So if something was in the middle of one of these, then basically we'd be saying that we don't know exactly where this is, but whatever value we pick, we're going to be within 0.2 millimeters. The idea is that even if something is in the middle, we can't say exactly where it is, and actually we'd have to round up or down to the nearest 0.2 millimeters, and that's our resolution. If you can imagine, then instead we use something like a micrometer. Micrometer, generally they tend to be a lot more accurate than a ruler, and you can maybe measure to 0.01 millimeters, let's say, using your micrometer. And so a micrometer would therefore have a higher resolution and would give you something, a more accurate reading. Now, does that mean you always want to use a micrometer? Well, not necessarily, because sometimes if you've got something very, very large, you don't want to be using a micrometer, because that's going to take you a very long time to measure something very big. It might not be appropriate. You might not have a micrometer big enough, and maybe more importantly, you might not need precision to that level. If you imagine you're measuring something absolutely tiny that's only a few millimeters long, maybe you want to use a micrometer. But if you're measuring something big that's a few meters, then you're probably better off with something like a ruler. So it's about choosing the thing that is appropriate as well. So that's random errors, and also actually choosing the right equipment. Now we want to talk about systematic errors as well. So systematic errors essentially are not random. They're errors that are produced every time you take the measurement, and they're of essentially a set quantity. And it's essentially, a systematic error is usually to do with how you've actually done the experiment, and you've done something, you tend to maybe have made a mistake that's introduced a systematic error, or sometimes it's just the nature of the experiment. There's going to be a systematic error in there which you can actually correct for. So random error you can never really reduce, and it's difficult to correct for it. Systematic error is something that is correctable, and it is something that tends to be set and reproduced every measurement. So for example, we have something called a zero error. Now a zero error basically refers to when you haven't set zero properly. So for example, if you take a pair of weighing scales, now weighing scales, when there's nothing on them, the needle, if you like, should be set to 0. Now sometimes this is actually not the case, and if you check your weighing scales at home and no one stepped on it and it should be 0, it will give you a value that's maybe, half a stone, or in this example, let's say 1 stone. That means that when you step on it, it measures starting from 1 stone. So maybe it says that you're 10 stone, but actually because of the systematic error, you're not 10 stone. It's introduced an error of 1 stone, and so you're actually only 9 stone. So hopefully that makes sense. That's your zero error, and that can be introduced in something like when you're weighing scales, or if you're measuring something and you don't start from 0, again you have a zero error. But you can correct for this if you actually know the zero error. You can correct for it. If you know that all your measurements start from 1 stone, then you can just take off 1 stone at the end. Okay, so next we want to come across a few different terms that sound very similar but have very different meanings. So the first one we come across is something called reproducibility. So if we say something is reproducible, what does that mean? Well, it basically means that if something is redone, if an experiment is redone by a different person and you get the same results. So you have an experiment, you redo it by a different person in a different lab or different environment, and you get the same results. That means that it is reproducible. Now the more common one is something that is repeatable. So if something is repeatable, it means you have your experiment and you can redo it by the same person in the same lab, same person / lab, and you won't get the same results. So if I basically do an experiment and I do it 10 times and I see the same results, I'll say it's repeatable. If you then take that same experiment, you go to your lab and you repeat it and you get the same results, we say it's reproducible. So hopefully the distinction is quite clear there. Okay, so now we come to the final section of this topic, and that is the one that students, to be honest, do tend to struggle with the most. And the reason for that is because it can get a bit mathematical, and this is the part that really is important when it comes to your practical exercises. So written uncertainty in orange there, not sure why, but let's go with it. So what do we mean when we say uncertainty? Well, the idea is that we can take a reading, we can take a measurement, and within that measurement there's a uncertainty within it. So we can't say for sure that that measurement is totally accurate. So for example, let's say we take a temperature reading and we get a temperature of 10 degrees Celsius in our room. Now we can't say for sure our temperature is exactly 100% 10 degrees Celsius. The reason for that is because what have we used to measure that? How have we measured that? Our methods introducing all these different errors, which means that there's a certain range of temperatures that we say could be within this. Even though our measurement says 10 degrees, it could still be something a little bit different. So the way we represent this is by we say the temperature is 10 degrees plus or minus, let's say 3 degrees Celsius. Okay, so we're saying that we've measured it as 10 degrees Celsius, but we're not completely sure it's 10 degrees Celsius, and we've given it a range. It could be plus or minus that. So in reality, we're saying it could be 7 to 13 degrees Celsius. Essentially, that's what we're saying. So that's uncertainty. Now, this is what we call absolute uncertainty. The reason why it's absolute uncertainty is because it's an absolute value. Okay, so when we write it out like this is called absolute uncertainty. The reason why it's an absolute value is because the unit here is the same unit as the unit of measurement. So we measured it in degrees Celsius and we give our uncertainty in degrees Celsius, therefore it's an absolute uncertainty. The next uncertainty, or the way we can kind of rewrite this, is if you were to write 10 degrees Celsius plus or minus 10%. Now we're writing this in terms of a percentage uncertainty. So as you can imagine, because it's written as a percentage, it's what we call a percentage uncertainty. Now, very, very close cousin, if you like, of this would be 10 degrees Celsius plus or minus 1/5. Yeah, 1/5, and this is what we call a fractional uncertainty. Now these two, what we're saying is these uncertainties are not absolute, they're relative to the actual measurement. Okay, so here we had an absolute uncertainty, we had 3 degrees Celsius, we're saying that's our uncertainty. If we change the measurement and say there was 15 degrees Celsius, our absolute uncertainty still might be 3 degrees Celsius, right? Now these two, they're relative uncertainties, the percentage uncertainty and the fractional uncertainty. So let's look at the percentage uncertainty first. If we say 10 degrees Celsius plus or minus 10%, then effectively we're saying that 10% is referring to this measurement in the first place. So effectively we're saying 10 degrees Celsius plus or minus 1 degree Celsius, because 10% of 10 is 1. So hopefully that makes sense. We've transferred our percentage uncertainty into an absolute uncertainty. Same thing we can do exactly the same thing with our fractional uncertainty. If our fractional uncertainty here was 10 degrees Celsius plus or minus 1/5, well, 1/5 of 10 is 2. So we're saying it's 10 degrees Celsius plus or minus 2 degrees Celsius. Okay, so hopefully that makes sense, the relationship between fractional uncertainty, percentage uncertainty, and how to change those into the absolute uncertainties, and vice versa. If you wanted to change 10 degrees Celsius plus or minus 3 degrees Celsius into a percentage uncertainty, how would we do that? Well, let's have a look. 3 degrees Celsius is equal to 30% of our measurement of 10 degrees Celsius, and therefore the actual, if we were to write that in terms of a percentage uncertainty, this would become, if we just move this out of the way, this is equal to 10 degrees Celsius plus or minus 30%. Okay, so I think hopefully that's clear now. Now the next part we want to look at is actually when it comes to combining uncertainties. So when we combine uncertainties, it's a little bit different. So generally what we have is when we take measurements, a lot of the time we build up measurements to calculate certain quantities. So let's say, for example, we want to work out the differences in speeds between 2 runners. So let's say we have a speed gun, we measure the speed of runner A. So runner A, you measure his speed as 15 meters per second. And runner B has a speed of 20 meters per second, and we want to work out what's the differences in speeds. Now, the first thing we need to take into account is the uncertainty. So, first of runner A, we use a certain speed gun, and it's got an uncertainty of plus minus 3 meters per second. And runner B, we've got an uncertainty of plus minus 2 meters per second. Okay, so we used 2 different speed guns to measure it. That's why we've got 2 different uncertainties from our 2 different speed guns. Now, if you want to work out the differences in speeds, we do 20 minus 5, and we'd get a measurement of 5 meters per second. That's the delta, right? That's the difference between these 2 runners. However, we need to take into account the uncertainties. Now, the way we do that is when it comes to adding or subtracting data, all we need to do to calculate the uncertainty of our calculation is to add the absolute uncertainties. So here, the absolute uncertainties was 3 and 2. So the absolute uncertainty of the new value that we calculated, the delta, would be plus minus 5, right? So 3 plus 2 equals 5, and so this becomes 5 meters per second plus minus 5 meters per second. Okay, so essentially we're saying that the difference could be anywhere from 0, so 5 minus 5, or 10. So 5 plus 10. 5 plus 5 equals 10. Okay, so that's for when you add different data points together and you want to work out the uncertainty of the actual calculation, then you just add the percentage uncertainties. Okay, so if you add or subtract, that's how you do it. Now let's say instead that you want to multiply. Let's say you do a calculation from your measured data and you want to multiply that together. So an example might be you have a force of 30 newtons and you have a mass of, let's say, 10 kilograms, and you want to work out, if I put this force of 30 newtons on this 10 kilogram mass, what would the acceleration be? So that will basically look like 10 kilograms here, 30 newtons here. Now, we can work out the acceleration by using the formula F equals ma. And we can rearrange that to get A equals F over m. So here we are doing a division. So this should actually read multiply or divide. So what we want to do is, let's say we measured the force. And we get a measurement of 30 newtons plus minus. And then we measure the mass, and again we measure this, let's say we use a scale, and we get a measurement of 10 kilograms plus minus 2 kilograms. Actually, let's make this 10 kilograms plus minus 0.5 kilograms. And now we want to use this information to work out not only the acceleration, but the acceleration with the uncertainty calculated within it. So first of all, to work out the acceleration, very simple. It's just acceleration equals the force over the mass. So it's 30 newtons over the mass of 10 kilograms, and that equals 30 divided by 10, 3. But it's not going to be 3 meters per second squared exactly. It's going to be 3 meters per second plus or minus a certain uncertainty. And how do you work out that uncertainty? Well, when you multiply or divide your data, then to work out the uncertainty of the calculation, you need to add the percentage uncertainties. So previously, when we added the data or subtracted the data, we had to add the absolute uncertainties. If you multiply or divide the data instead, we have to add the percentage uncertainties. Okay, so how do we go about doing that? Because uncertainties that were given, so the uncertainties that were given in absolute uncertainty. So we need to convert these first of all to percentage uncertainties. So let's take the force first of all. So the force equals 30 newtons plus minus 3 newtons, and that is equal to 30 newtons plus minus 10%, because 3 newtons is 10% of 30. So it's 10% of our actual measurement, and therefore the uncertainty is plus minus 10%. We could do the same thing with the mass. So the mass was equal to 10 kilograms plus minus 0.5 kilograms. And so that is equal to 10 kilograms, and we just need to convert this to a percentage again. So 0.5 kilograms. What is that as a percentage of 10 kilograms? Well, 0.5 kilograms is actually 5% of 10 kilograms. And if you're not too sure how to work out what that is as a percentage, it's quite a simple formula. It's just 0.5 over 10 times by 100%. That's it. So it's just whatever the absolute uncertainty is over the actual value times by 100%. And if you plug that into your calculator, you should get that it's going to be 5%. Okay, cool. So now we've got the percentage uncertainties for both of these. Because we did force divided by mass, that means that we did a division, and so we need to add the two uncertainties of force and mass together, but we add the two percentage uncertainties, and therefore the acceleration value that we get, and we worked it out, and the acceleration was 3 meters per second squared. But we can add an uncertainty of plus minus 15% because we added both of those together. And if you want to, we can then rewrite that, because 15%, we can put that as a absolute uncertainty. So 15% of 3 meters per second would be 0.45. And again, if you're not sure how to work that out, it's just 0.15 multiplied by 3, and you can put that into your calculator. And so we can rewrite that in terms of an absolute uncertainty as 3 meters per second squared plus minus 0.45 meters per second squared. Okay, cool. So that is basically the most difficult bit, or the bit that students find the most confusing, is your absolute and your percentage uncertainties there. And in particular, this bit of when you do something with your data, when you do a calculation with your data, how do you work out the uncertainty of the final result? Well, if you're adding or subtracting, then you add. If you're multiplying, then you add the percentage uncertainties. Another one is if there's a power. If there's a power, essentially it's the same thing as multiplying. So if we imagine we have a circle, and we measure the radius of the circle as 3, but we measure it as 3 centimeters plus or minus 1 centimeter. Let's make it a bit simpler, plus or minus 0.3 centimeters. How do we actually work out the percentage uncertainty in the area? Well, the area equals pi r squared. So here we want to square the radius, so what would the uncertainty be? Well, squaring the radius is the same as doing r times r, so it's a multiplication. If it's a multiplication, we add the percentage uncertainties. So the percentage uncertainty of r is 0.3 as a percentage of 3 is 10%. So this we can rewrite as 3 centimeters plus minus 10%. So the uncertainty in r is 10%. The uncertainty in r is also 10% because it's the same thing. And so the area would be equal to pi r squared, or pi times 3 squared, plus or minus, we add the two percentage uncertainties together, so it's plus or minus 20%. Yeah, so that's the percentage uncertainty. And if you wanted to actually work out the absolute uncertainty, all you would do is calculate that and then work out 20% of that, and you can rewrite it in terms of the in terms of the absolute uncertainty. The next thing we're going to look at is actually where these uncertainties can come from. So there's quite a good relationship, or a relationship that you should be aware of, between resolution and uncertainty. So as you mentioned before, we alluded to before with resolution, let's say you have a ruler, and this ruler, you got 1 centimeter here, you got 2 centimeters here, you got 0.5 in the middle, and you got no other readings. Now this ruler you can measure up to the nearest 0.5, right? Nearest 0.5 centimeters. And so if there was something in the middle, you wouldn't really be too sure. It could either be 0.5 or it could be 1. Sorry, this should be 1.5. It could either be 1 or it could be 1.5. But you're not too sure where it would lie. So you'd either say that it's 1.5 or you'd say it's 1. So the uncertainty really is actually half of the smallest division. So whatever this is, because the reason for that is, if you imagine your object was instead over here, then it'd be a little bit more than 1, but it wouldn't go up to 1.25, because once it's 1.25, or if it's on this side, then you round up to 1.5. If it's on this side, generally you round down to 1. So the error of the actual value would be, in either case, it would be up to 0.25, because when it's at 1.25, you're not really too sure which side should you round up or should you round down. So instead, that's the maximum error that could be, is 0.25. So the uncertainty we say is 0.25. Okay, so the easy way to remember that is just half of the smallest division, right? So the smallest division in this case was a length of 0.5 centimeters, and so half of that is 0.25, and so any error here would be plus or minus 0.25. The final bit which you do need to know is all about uncertainties in graphs. Now, this bit is all to do with lines of best fit, and so naturally I'm going to draw some wonky lines on now. Now, when you have a graph, generally you can plot your points. So let's say we plot our points like this. But with your points, you can actually draw on the uncertainty. So let's say when we took these measurements, we worked out the uncertainty of each measurement. And so the maximum value that this measurement could take is up here, and the minimum is down here. And let's put on some numbers. So let's say we measured the length of a spring, and we measured it each time, and we added mass on the end. So let's say we measured it, we got measurement of 3 centimeters. But let's say obviously there's going to be uncertainty within our measurement, and so the maximum it could have been was, let's say, 4 centimeters over here, and the minimum it could have been was 2 centimeters over here, right? So the error was plus or minus 1 centimeter, or the uncertainty was plus or minus 1 centimeter, and so we can draw our error bars on like this. And the same thing here, right? So you could say if this was the same, then that would be plus minus. Let's say this time we used a different apparatus. We've got a smaller uncertainty, and this time we had a large uncertainty on the top end and a smaller uncertainty on the bottom end. And depending on how you've done your measurements, you could get these different error bars. And we won't go into detail how you get these error bars first of all, but essentially the idea is that when you go to draw your line of best fit, your line of best fit has to pass through all of the error bars, right? So sometimes it won't be possible to make it pass through all of the points, but it has to at least pass through all of the error bars. So here, if we were to draw a line of best fit, we can actually do this with a ruler. And obviously, you should be doing it with a ruler anyway, so it makes sense. And so we draw a line of best fit, and I think that's, yeah, you know, that's a pretty decent line. So if we draw the line on here, cool. So that's the line we get. So that's our, if you like, our optimal line of best fit. Now we want to make the lines of best fit, which would technically still be classified as lines of best fit in that they would still go through all of the error bars, but would be basically the worst possible lines of best fit that we could make. So what do we mean when we say this? So let's choose a color. Let's go with blue. Let's take our ruler again, and we want to make, first of all, the steepest possible line of best fit. The way you do that is you let's make it a bit easier for ourselves by changing this error bar. So we'll just change that a bit, so just don't worry about that. So we want to make the steepest possible one. The way we do that is we go to the first error bar, we go to the bottom point, and the last error bar we try to go to the top. So like this. So go to the top of this one and the bottom of this one. That's the steepest one. So that's one of our worst possible lines of best fit, is the steepest possible line of best fit. Next we try to go for the shallowest possible line of best fit. The way you do that is you go to the top of your first one and the bottom of your last one. There we go. So now you've got your two different lines of best fit. So you got technically the orange one we call the line of best fit, the line of best fit, and the blue ones generally we call the line of worst fits. Okay, so we've got two different lines of worst fit here. They could both be lines of worst fit. The worst one would be the one that's the furthest away from the line of best fit. How do you work out which one's the furthest away? Well, we do it by calculating the gradient. I'm not going to get into how you calculate the gradient, you should already know that. But essentially then, what you can say is that the percentage uncertainty is equal to the best gradient, so the gradient of your line of best fit, minus the worst gradient, and you should divide that by the best gradient. Okay, and obviously you times that by 100% as usual to get your percentage. So this gives you your percentage uncertainty in your measurements by using the actual graph. Okay, so that's the other way that you can do it. Yeah, so that is basically it. There is one more section about estimation of physical quantities. If you do want to go through that, then let me know. But that basically recaps and summarizes everything you need to know when it comes to measurements and their uncertainties. So hopefully that was useful. If there's anything else you want to go through in more detail, anything that wasn't clear, let me know. Otherwise, I will see you in the next one.